Good morning, everyone. We're going to wrap chapter 12 up this morning and then get into some review problems. We could probably also take some Q&A if there is any specific topics you guys would rather hear today. Also, and this will be on a slide later, but there's a review session by me, like a Q&A session online like we did for midterm 4. I think it worked out really nice being online where you guys could ask questions. We can kind of drive the discussion of what we talk about in the review based on what you guys want to hear about in the chat feed. So we'll do that Thursday, 10:30 to 12:30. There's a review here, 1 to 3 p.m. in person and online by Dr. N that had done reviews for midterms 1 through 4 as well. So if you want to check that out, you can do that too. All these things will be recorded and posted so you can watch them after the fact. But getting back into chapter 12, we're talking about crystalline versus amorphous solids. The idea of a crystalline solid is that the atoms in the solid adopt a very regular repeating pattern that's going to give the solid a more brilliant appearance. It'll be brighter. As a result, it'll look like what you think of as being a crystal. And so things that do this, we'll see these are mostly our ionic compounds. These will be things like the covalent network solids. And then these will be metals, often form into a crystal regular repeating pattern about their atoms. And then our amorphous solids, these are going to be mostly our molecular solids. Okay, so let's take a look at the difference between a substance that's crystalline or amorphous depending on the situation. So quartz is actually, this is what quartz looks like here. So this is just a simple picture of quartz. And what quartz is just an arrangement of SiO2. SiO2 you would think would be like CO2. CO2 being a linear molecule is actually very much unlike SiO2. SiO2 forms these networks where a silicon atom bonds to 2 oxygen atoms and then makes this type of a ring structure where the atoms kind of make a ring of varying sizes. And then the size ring in quartz is very repeatable. So in quartz, you have a very regular pattern of like roughly 6-membered ring silicons with oxygens in between them. And so quartz, while it's not a perfect crystal, so you see some imperfections still, that's why the color is not one single color, and it's not necessarily very bright as a result in terms of looking like a red crystal or a blue crystal, but you get a more brilliant appearance for quartz because you have more of a regular repeating pattern of these ring sizes of the SiO2 units throughout the molecule. Then if you want to make glass, glass is also comprised of SiO2, but it's what we call amorphous SiO2. That's where you melt down the quartz. So you take a piece of quartz and you heat it up to a high temperature such that it melts, and then you let it lay flat, and then you freeze it out. And then when you freeze it out, the rings freeze in whatever shape they happen to be in. So you get a varying size set of rings of your SiO2 units, so you don't get that regular repeating pattern. So now when light hits the SiO2, it actually more likely just goes straight through as opposed to deflecting off in some regular way. So the idea of a crystal is a crystal that has a regular pattern deflects light in a very similar fashion, giving it that more brilliant appearance. SiO2 that's been melted down into glass doesn't have that property because it's no longer crystalline, and that's what we describe as being amorphous. So I just wanted to describe the difference between crystalline, regular repeating pattern, versus amorphous, more of a random structure. And so just to give you a brief look at what some different ionic compounds look like, and again, I doubt you'll see anything like this on the test in terms of, looking at different crystal structures, but I just wanted to show you that that ionic compounds have this crystalline structure. Sodium chloride has an arrangement of its ions where the positively charged ions are right next to the negatively charged ions. And like we mentioned this way back in chapter 2 and chapter 4, there just goes plus minus in all 3 directions for NaCl with a particular pattern. Now, not every ionic compound takes this particular pattern. So you can see other ionic compounds like cesium chloride takes a pattern kind of like what we were looking at for the metal structures last time, where you have a cesium in the middle, then you have 8 chlorides on top and bottom. And so you have a cesium in the middle of a box, and you end up forming 4 bonds on top and bottom to chloride ions. And so CSCl is just a little bit different in terms of the nature of the way its atoms arrange themselves in 3 dimensions. And again, I don't expect that you memorize that, but I think it's interesting to see that different types of ionic compounds take on different shapes. Now, cesium happens to be very big. So if you recall from top to bottom, cesium is going to be a big ion, and it's going to wedge the smaller chloride ions above and below it. Sodium is a little bit smaller, so it just goes in a more direct pattern in terms of how its atoms are arranged. Zinc sulfide forms an even trickier to understand structure where you have zinc atoms kind of in the middle of a box, and they're forming these like four-membered almost connections to sulfide ions throughout the structure. But I think that the issue is the point is to see that there's different types of crystal structures that you get for different types of ionic compounds. Calcium fluoride, if you have a ratio of 1 to 2 ions, you're going to get an even different type of configuration. It kind of looks like the zinc sulfide structure, but if we had atoms, 8 of them inside the box forming those four-membered ring interactions. So again, I don't expect that you memorize these pictures or that you'll even really see them again or do much with them, but just kind of trying to show you that different types of ionic compounds have different types of repeating patterns. And the idea of this box, these boxes here, is that if you picture a box next to a box next to a box, that's the idea of the crystal, is like that's the repeating pattern. So a substance that has a crystal structure has something in a box that would repeat to the left, to the right, on top, on bottom, in front, and in the back. So it's just trying to show you that you can take this box and kind of lay them in all 3 dimensions and then imagine kind of a crystal emerging from that structure. We also get this for things like diamond, for the 3-dimensional array of tetrahedral carbons for diamond versus the 2-dimensional sheets of graphite, where graphite has 2-dimensional sheets of carbon atoms that then are connected by an intermolecular force. So graphite's very interesting in that we have covalent network bonds in 2 dimensions, and then a sheet attached to the other sheet above it just by the electrostatic force of attraction, like a dispersion force. And so then when you use a graphite pencil, I think we've mentioned this before, that these sheets just slide off of each other. So when we slide a pencil, those individual sheets of graphite are just sliding off each other. In fact, people have done experiments where they take like a piece of Scotch tape and they kind of can remove one single layer of the graphite. They call that graphene. So graphene would be just a single layer of those benzene rings in 2 dimensions. And they've done experiments to try to visualize what the atoms look like. And they look exactly like you think, 6-membered rings of carbon atoms. Now, metals, again, just kind of showing you that they form crystal structures too. We talked about those previously, so I'm not going to go back through those here. But metals form, with a couple of distinct type of patterns in terms of their arrangements as well. And then when you think of the nuclei in some arrangement, you still have the electrons kind of swimming around those structures. You might recall that sea of electrons model. Okay, so that wraps up our coverage of chapter 12. I just wanted to give a quick overview. The main idea, I think, from chapter 12 is just trying to understand there's 5 different key types of solids that we talked about. A quick review from last time was, we talked about molecular solids, ionic solids, metals, covalent networks. The one we didn't mention today was polymers. In terms of polymers, they generally don't form a crystal structure because they have more longer chains, look like more molecular compounds that are just much bigger in size. So they're more amorphous in their structure. But understanding some of those key properties, that the molecular solids, low boiling point, low melting point, ionic compounds and the other covalent networks, metals, high melting points and boiling points, polymers kind of in the middle, variable properties, and then conductive property. We only get the conductivity with metals. Ionic compounds themselves aren't very conductive unless you put them in water, and it makes water more conductive. So those are just some of the details from chapter 12 that I think are most important, and then a few pictures to hopefully help us understand a few extra details from the chapter were also included in the discussion. So I think that the primary focus of chapter 12 for the exam, if you look at the practice exams, is primarily on the first set of slides on just the different types of solids, and then maybe being given some facts about a solid and trying to determine what type of solid it is, or some of the behaviors given the type of solid that you expect. Okay, so final exam is Monday morning here in this room. It's a 50-question exam. You get more time than the midterms. So it's a 100-minute exam. So there's 50 questions on the exam. And it's going to be about 8 questions from each of the midterms 1 through 4 topics in review. So about 32 questions from those 4 midterms in terms of review. They won't be questions directly from the exams, but from the coverage of those topics of the exam. So about 8 questions from chapters 1 to 2, from 8 questions from 3 to 4, 8 questions from 5 to 6, and then 8 from 7 through the last couple sections in chapter 9. The last 2 sections in chapter 9 we covered after midterm 4. So 9, 7, and 8, we'll see 2 questions from those sections. We'll see 2 questions from chapter 12, a very brief coverage of chapter 12, so just 2 questions, then about 7 questions from chapters 10 and 11. And so, like we said here, the exam is cumulative, of course. We're trying to focus on some of the bigger picture items instead of the little nitty-gritty items. So in terms of reviewing, if you haven't spent much time yet reviewing material, chapter summary is a great start at the end of each of the chapters of trying to review a chapter summary, go review some problems on the topics that seem a little bit less clear to you or less memorable. Hopefully we'll hit some of those here today or tomorrow in our review work that we look at too. There's 3 practice exams posted. One's a Carmen practice exam like the other practice midterms have been, and then there's 2 like PDF practice exams. I have some practice stuff on my end too, so if you go to the daily quizzes, there's some practice final content there. 1 or 2 of my practice finals are, I think, duplicates of what the department gives you. So 1 or 2 of my practice items I think you will already have seen with the department practice exams. Check out the sample info that's provided. We provide a ton of equations. Check the equation sheet out if you want to see which ones, but it's most of the summarized equations from the end of each of the chapters. And so then, yeah, try to figure out the topics you need to study the most. Every student in the room probably has a chapter or a topic that they understand less than the others, so try to figure out what those ones are and spend more time reviewing those topics if possible. And then some additional office hours today. The usual ones are 9 to 11. I'll also have one from 2 to 3. These are upstairs in this building, 2047 McPherson Lab. If you want to, just stop by. You don't, of course, need an appointment or anything. And then Thursday, just online on Zoom for my review, 10:30 to 12:30. And then 1 to 3 in person. I think it's in this room. And then also on Zoom or video afterwards. So we'll be posting these videos as usual. And then Friday, I'll have an office hour just in the afternoon, 1:30 to 3. So stop by if you have questions then. So that is the sort of set of final information. Before I get into any topics that I have on my review packet, is there any general questions I can take before moving on? Yeah.
Will you post like a sample review packet for the final, or is that just can that be done by using like the daily quiz?
Well, I mean, I think that there's a practice final module that has a practice final. I think it's live. Is it live? Okay. Yeah, sometimes I forget to hit the button to make these things actually viewable by you guys. But yeah, so there's a Carmen practice final. There's 2 additional practice final PDF exams. And then on the daily quizzes, there's a bunch of practice finals in there and practice items.
I'm saying for like the exam, like information sheet.
Like the sample info? Yeah, that's in the practice exam module. So if you go to the practice final, you'll see the scratch paper booklet. Yep. Yeah, and then like for chapter 10 is a big one with a bunch of equations. You get essentially all the equations from the end of the chapter, I believe, is how they determine what equations to give. Any other questions? Any topics that you guys want to hear more than others? Might be easier on Thursday to kind of take more individualized questions. Okay, let's actually just start with this pack and kind of go linearly. If, maybe we'll stop closer towards the end and see if there's anything you guys want to hear today before we take off. So let's look at a phase diagram. And so the first thing I think when you see a phase diagram that I would want to take note of is kind of which axis is the pressure, which axis is the temperature. And so at low pressures, low temperatures, you would expect the substance to be either a solid or a gas usually. So if you're at a low temperature, usually we're going to be over here in our diagram thinking low temperature, low pressure, we have a solid. Increase the temperature, we can sublime. If we raise the pressure a little bit, this is standard atmospheric pressure at 1 atm, then we can undergo the process from solid to liquid to a gas. We call that like a normal process of having a normal melting and a normal boiling process. We have the triple point here. This is the point at which you have the coexistence of the 3 phases. I think the big idea of this point here is if you go below the point, then you can only have the solid to gas or gas to solid transition take place. So only sublimation or deposition. And if you go above this point, then you can have solid to liquid. And then our critical point here, this is just our supercritical fluid. You can go above point C in temperature and pressure. It's just then you start to lose whether or not the substance is really a gas or a liquid. So we call that a supercritical fluid. It just means you have tandem gas-liquid properties for the substance. And then the other thing to take note of is the kind of directionality of this curve here. This is the melting point curve. And so then this curve here is telling you if you pressurize a solid, so pressurizing is going up. if I pressurize the solid, I'm going to turn it into a liquid. And that's kind of abnormal. It's not normal. Most of the time if you pressurize a liquid, you usually can turn it into a solid. Because usually taking a liquid, pressing the atoms closer together is turning it into a solid. This is doing the opposite. So this is kind of like an inverse melting point curve showing us probably a property like water has this general property that if you think of water, it's the ice form is more dense than the liquid form. So if you, the ice form is less dense than the liquid form. If you take ice, press the atoms closer together, you can turn the substance into a liquid. Okay, so let's take a look at our choices here. The solid has a higher density than the liquid. Well, I think we can already rule this answer out by the fact that adding pressure to a solid is taking the solid and compressing it. That's increasing its density. If we increase the density of the solid, it becomes a liquid, or can become a liquid. And so that means the liquid has the greater density. So the liquid phase has the greater density. Okay, and so then statement B, sublimation and deposition are the only phase changes possible at temperatures and pressures below point B. Point B is noted here, that's point B, so that's the triple point. That's a true statement. So if you go to temperatures and pressures below the triple point value, then the only phase change that can take place is this phase change here. And then you can phase change by changing temperature or pressure. So you can imagine phase changes. Let me erase a little bit here. So you can imagine if you have a substance here at that temperature and pressure, if you add pressure, we can solidify. If you keep adding pressure, we can liquefy. And then if you take this pressure here, lower the temperature, we can solidify. So you can have phase changes by changing temperature or pressure. Okay, so that is a true statement. We're looking for the false statement. I think we already found it in A, but let's make sure we understand the other statements. No phase change occurs when the liquid phase is compressed at constant temperature. So if I take the liquid phase, so liquid phase is here. If I take that phase there and I add pressure and I go upward in pressure, notice that I always stay a liquid. So there's no phase change going on when I take anything on the liquid side and then increase the pressure straight up. And so no phase change will occur. So that's a true statement. I hate the true false statements, like identifying the false, because it's like, that's a true statement, which makes it not the right answer to the question. When heated at 1 atm, the substance will first melt and boil. So at 1 atm, we can undergo warming to melt, warming to boil. So that's true. And it is indeed possible this is water. Water is one of the few substances that has that inverse melting point curve, one of the few substances that has a density of its liquid greater than the density of water being greater than the density of the solid. So that's a true statement as well. So the only false statement is statement A. Okay. If there's follow-ups, feel free to chime in as we go. All right, so vapor pressure of a compound, CH3F, is 3.3 megapascal. And then the vapor pressure of a different compound is lower, it's 0.5 megapascal. First glance, you may be thinking, what the heck is a megapascal? Just note that I think we're being told this information here just to be able to see that this compound here has a lower vapor pressure than this compound. So it's just giving us some numerical data, but it's really just for us to see that the CH3F is higher, CH3Cl is lower. And so then what would explain this trend? Well, let's think for a minute about the intermolecular force that these two compounds would have. They should both be tetrahedral molecules. And so we can sketch some Lewis structures, or some molecular geometries, really, is what we're sketching here. So they're both tetrahedral, so I'm trying to sketch tetrahedrons to show what these substances look like. They both should be polar. Neither one form hydrogen bonds because we don't have H directly attached to a fluorine, oxygen, or nitrogen. And so these both should have a dipole-dipole force and a dispersion force. And in the case of CH3Cl, we might be thinking it at least has a bigger chlorine, so it might have a greater dispersion force, but it's also probably less polar because the carbon-chlorine bond's doesn't have as great of electronegativity difference. So it might be So this compound here might be lower in dipole-dipole force, but higher in dispersion force in terms of thinking of those two properties. So it might be less polar, but it might pick up some extra dispersion force just by virtue of being bigger, having a larger chlorine instead of a smaller fluorine atom. So now, does having a lower vapor pressure for the CH3Cl, so this compound here has a lower vapor pressure, does that mean it has a stronger or weaker intermolecular force of attraction with itself? So vapor pressure is the one compound that's inversely related to intermolecular forces. So if you strengthen intermolecular forces, you lower vapor pressure. The idea is, imagine a liquid. A liquid, in order for it to have a vapor pressure, means a liquid molecule has to escape into the gas phase. The escape into the gas phase is going to take more energy with the stronger intermolecular forces. So if we have a stronger force of attraction between the molecules, it's going to be harder for a molecule to escape into the gas phase. Therefore, it will have a lower intermolecular force. And so CH3Cl has a lower vapor pressure. Therefore, it has this stronger intermolecular force between these two compounds. So the force of attraction between adjacent molecules of CH3Cl has a stronger intermolecular force of attraction. So now why would that be? Well, it must be because that dispersion force won out. So it must be when we're thinking, okay, if I'm looking at the two molecules, I probably couldn't predict this because, like we said, CH3Cl should have a weaker dipole-dipole force but a stronger dispersion force. How do we know which one wins out? Well, once we take a look at some data and see that CH3Cl has a lower vapor pressure, we're like, oh, that must mean it has a stronger force of attraction, so that it must have a much stronger dispersion force that overcomes the loss of dipole-dipole force due to being less polar. And so the explanation here for the difference, it really doesn't have anything to do with electronegativity difference, because if it did, we would probably think CH3F would have the stronger intermolecular force, because if it was just based on electronegativities, we would expect that the more electronegative CH3F should have had a stronger dipole-dipole force, and then it would have had the lower vapor pressure, but that wasn't the case. The London dispersion forces in CH3Cl, that is the explanation. So the word London is often not used anymore, so often we just call it a dispersion force, but we used to call these things London dispersion forces. I don't think our book uses that word anymore, but some old problems do. But this is just what we think of as being the dispersion force. So the simple dispersion force in CH3Cl is greater than CH3F because it's bigger. That's going to be the primary factor that leads the intermolecular force in CH3Cl to be stronger than CH3F. And it's not the dipole-dipole force, because if it was, again, we would have had a flip and CH3F would have had the lower vapor pressure. This has nothing to do with bond strengths. So the strength of bonds is completely irrelevant here because we're not breaking covalent bonds. When you take a substance, water, CH3Cl, CH3F, and you vaporize the substance, if you take the liquid, vaporize it, you're breaking the intermolecular forces. You're breaking the dipole-dipole force, the dispersion force, whatever the intermolecular forces are between two molecules you're breaking, but of course we're not breaking the covalent bonds. We're not breaking these bonds here, those remain intact. So those bond strengths are completely irrelevant to vaporization. There's no hydrogen bonding present in any of these molecules, and wherever I took this question from had an option of the last one, which is kind of irrelevant. So yeah, the only option here that makes any sense is that it's the dispersion force being higher in CH3Cl that we can reason out given the data about their intermolecular forces through their vapor pressures. Any follow-ups on that one? Okay, so sometimes we can predict, like when we're looking at like O2 versus neon, we can compare that O2 is bigger because it has two atoms, neon's smaller, just has one atom, that O2 should have the higher attractive force, higher melting point, boiling point, etc. But sometimes we have to be given data like in that previous problem. So sometimes we can't predict the trends, but we can tell you some data that helps you predict the trends. So what happens when CH2F2 evaporates? Do we have dispersion forces overcome, dipole-dipole forces, or covalent bonds broken? So imagine you have a liquid sample of CH2F2. So if I'm thinking of a Lewis structure, and I'm kind of intentionally drawing the Lewis structure this way, hopefully we spot it as being tetrahedral right off the bat. But if you're not sure if it's tetrahedral or not, you kind of start by drawing a Lewis structure, attaching the electrons or giving electrons to the fluorine atoms. That uses all of our electrons. If we want to double check, we go 4 valence electrons for carbon, 2 for each of the hydrogens, 2 times 7s for the fluorines. And then that gives us a total of 20 valence electrons. And I have 8, 16, 18, and 20. So just making sure we're good on the Lewis structure side. But the real Lewis structure isn't square planar. So when I'm looking at this Lewis structure, we might incorrectly think that this molecule is nonpolar because we might think those dipoles cancel. But the dipoles don't cancel because that bond angle is really not 180 degrees. This bond angle is really 109.5 degrees. And that's because the real structure looks like this. And it doesn't matter where you put the fluorines, there's still, like every bond angle here is 109.5 degrees. So I could have put the fluorines anywhere on the 4 positions here as long as I put 2 and then 2 hydrogens in the other spots. And so this molecule here, the thing we need to see is that it has dipole-dipole forces because it's polar. So any molecule that's polar has a dipole-dipole force. Okay, and so any molecule that's nonpolar doesn't have the dipole-dipole force. So if we were to determine that CH2F2 was nonpolar, then it wouldn't have the dipole-dipole force. But since it is polar, then it has the dipole-dipole force and of course the dispersion force. So when we have a sample of CH2F2, we have all these molecules adjacent to each other. We have to break those dispersion forces and the dipole-dipole forces. Of course, we're not breaking the covalent bonds like we talked about in the above example. So we're breaking 1 and 2, and then not the covalent bonds. There's no hydrogen bonding here either. An option of hydrogen bonds would have been a good choice just to make sure that you see there's no H bonds. So hydrogen bonding, I need a hydrogen directly bonded to fluorine. We don't have that in this molecule, so therefore it doesn't form that strong intermolecular force called hydrogen bonds. Any follow-ups? So surface tension, most of our properties in chapter 11, with the exception of vapor pressure, are direct relationships. So surface tension is directly proportional to strengths of intermolecular forces. And that's because surface tension is the energy required to break a surface. So it's the energy required to separate a surface and break it. And the stronger that attractive force is, the more energy has to be applied to break the surface. So the stronger the intermolecular force, the higher the surface tension, the higher the energy required to break the surface. And so what we see here are what this is meant to show us is a branched hydrocarbon. A branched hydrocarbon is one that looks like this. So that's 1, 2, 3, 4, 5, 6 carbons. That would be an isomer of hexane. We didn't teach you about sketching these Lewis structures and naming these things. We could have, but we didn't do that back in chapter 2. But I think the idea would be that this should have the same basic formula as taking 6 hydrocarbons in a row. Like what we did talk about is how this hydrocarbon here, so CH3, CH2, 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 and then a CH3, that is what we would call hexane because it's C6H14, and that's hexane. And that this is just an isomer, same formula of hexane. And so we can at least spot the isomer, but now this is what we call a branched hydrocarbon, and branching weakens intermolecular forces. It's going to be more easy for hexane, we sometimes call this N-hexane, but it's easier for the straight chain hexane to interact with another hexane molecule because they can more easily push their electrons around and induce a dipole moment. If I have a branched molecule, I don't know what's good. But if you have a branched structure, it's going to be harder for that branched structure to interact with another molecule of itself and induce a dipole moment just because the atoms can't get close together. They can't get as next to each other as they can in the straight chain version to induce those dipole moments to create that dispersion force. And so we get a weaker force of attraction in the branched hydrocarbons. We get a lower intermolecular force for the branched hydrocarbon, and we get a stronger intermolecular force for the branched hydrocarbon. So which member of each pair has the greater surface tension? Well, that would be the straight chain and not the branched structure. In the case of CH2Br2 versus CH3Br, they're both polar, because they're not maybe very polar, because the CBr bond's not as polar as like a CF or a CCl bond, but we do have what we think of as being polar molecules, but we have a bigger molecule because I have 2 bromines instead of 1. So I get a higher dispersion force for CH2Br, so that's going to give that compound a stronger force of attraction just based on having a higher dispersion force. So when we're comparing 2 molecules that are both polar, the one that's going to be a lot bigger than the other molecule is going to have a stronger force of attraction based on that size. Each bromine atom's like 80 grams per mole. That's going to add a lot of extra dispersion forces. And so then water at 25 or 75 degrees, this is an interesting question too, of when we heat up a sample, the molecules are moving around faster. I don't know if we've thought about this before. But as the molecules are moving around faster, it's going to be easier to separate them than when they're slower and they're having that force of attraction. So the higher the temperature, we already have the molecules that are moving around faster. It's going to be easier to break the surface at the higher temperature. So the lower temperature water, think about how hard it would be to break the surface of water if it was frozen. So if we go all the way frozen, it's really hard to break the surface of water compared to the liquid. So going to a lower temperature is going to strengthen that surface. And so it should be the straight chain, CBr2, water at the lower temperature. So another phase diagram question. This is for UF6, uranium hexafluoride. And so I'm just kind of looking at a few details. 1 ATM, we'd go solid direct to gas. Above this point here, we could have the normal solid to liquid to gas. Okay, so which statement is true? UF6 sublimes at atmospheric pressure. So at atmospheric pressure, UF6 can indeed sublime. It would sublime at a temperature of about 50 degrees. At 80 degrees C and 1.5 ATM, so you can go to 80 degrees here, and then 1.5 ATMs right in the middle. It'd be right about here. Only the gas is present at equilibrium. That seems true too. So we have only the gas present, and then we have both statements being true here. Okay, so with the phase diagram, you can go to a given temperature and pressure and just see what phase are we at. Are we in the gas phase, liquid phase, solid phase? If we happen to have found ourselves right on the curve, if we find the temperature and pressure that's on the curve, then that's an equilibrium point between those 2 phases. Let's look at some chapter 10 questions. Consider a cylinder with a movable piston that can expand against the atmosphere. So something like this. And then the initial pressure, volume, and absolute temperature inside the cylinder are P1, V1, and T1. What is the new temperature of the system when the pressure is increased to 3 times its initial value? So P2 is equal to 3 times P1. And then the volume is decreased to half its original value, which is V2 is 1/2 V1. And so the question is, what is T2 equal to? And so if we think of the pressure-volume relationship from our ideal gas law, our P1 V1 over T1 will be equal to N times R, where N's not changing because we have an airtight cylinder. So N and R are our constants. And so then N and R will also be equal to our new set of conditions after the fact. And so then that makes P1 V1 over T1 equal to P2 V2 over T2 because they're both equal to N times R. So that's how we get this equality here to work out to be true. So we can have that equality. So anytime you have 2 or more sets of variables that are constant, variables are changing, and then the other values are constants, you let the other values be constant, and then you set those variables equal to those constants, The new set of variables have to be equal to the same set of constants because we have to still follow the ideal gas law equation, so they have to equal also n times r, making them equal to each other. And so then if we rearrange this equation to solve for T2, we would have T2, let's put T2 over here, and then let's put T1 over here to multiply to both sides, and let's divide both sides by P1 over V1. So I'll have T2 equal to T1 P2 V2 over P1 V1. It's weird algebra, I'm just dividing both sides by P1 V1 and doing the rearranging to solve for T2. And so what I can then do is I can plug in 3 times P1 into my equation for P2. So T1, 3 times P1, a half times V1, just plugging in the V1, and then divide by P1 V1 still. So I cancel out the symbols for P1 and V1. So then I have 3 times a half times T1 is equal to T2. So I have T2 is equal to 3 halves times T1. Okay, weird problem, but so what this problem is looking at, it's saying if I'm going to triple the pressure but cut the volume in half. So to triple the pressure, if we're just thinking about leave the volume alone. If I wanted to triple the pressure, I got to triple the temperature to do that. And then if I at the same time got to take the volume and cut it in half, I then have to take that temperature and cut it in half. And so it takes me to 3 halves of the original temperature. So it's just trying to see how do we need to change these 3 variables relative to each other to have the ideal gas law still hold up, to still have those set of variables equal to n times r, would have that T2 is equal to 3 halves times T1. So which molecule escapes from a pinhole the fastest of the choices below? What do you guys think? Now, sometimes the answer E looks good because you're like, well, yeah, why wouldn't they all escape at the same rate? Well, each gas has its own velocity because the gases have different molecular weights. The velocity, kind of the average velocity or a way to calculate a weighted velocity for the average kinetic energy of the molecules is this equation here. It's 3RT over molar mass. I doubt you'll have to plug into this equation, but if you do, just remember, just plug everything in SI units. So this equation here, you'd use 8.314 joules per mole Kelvin, because joules an SI unit, ATM is not, so we don't use the 0.08206 version of R here. Of course, temperature goes in Kelvin, and then molar mass goes in kilograms per mole, because kilograms is the SI unit. So if you want SI units for speed to come out of this equation or for velocity, you got to plug SI units in to get those out. But anyways, the idea of this equation here is to see that if you have a lower molar mass for a substance, it's going to have a greater velocity, set of velocities on average. So the lighter the particle, the faster its velocities will be at the same temperature compared to another gas. And so that means helium of these choices, because it's the lightest particle, will have the fastest velocity. And so the fastest velocity of these gases is helium, meaning it's going to bounce around the container very quickly. It's going to have more of a probability of hitting the pinhole. It's going to leave the tire or the pinhole in this gas sample the fastest. The most massive particle here would, I guess, be O2, because it's 32 grams per mole. Water is 18 grams per mole. CH4 is 16 grams per mole. So O2 would leave this pinhole the slowest because it's moving around slower, so it just has a lower probability of hitting the pinhole. So it's going to leave the cell the slowest. Let's think about densities under a set of conditions. So density, this is an equation that's on the sheet. So if you need to look this up, you can look this up on your equation sheet. But it's pressure times molar mass divided by RT. Let me rewrite molar mass. So pressure times molar mass divided by RT. Again, it's on the equation sheet if you need to double check it. We could derive it, although I think if I'm gonna give you the equation on the sheet, maybe we don't need to derive it. But if you recall, this just comes from PV is equal to nRT. And then taking N as M over molar mass, density is M over V, and doing some rearranging. But density is pressure times molar mass divided by RT. STP is just a trick question in some regards. I don't know if we'd even ask about this on the test, but I've mentioned other tests like to see if you know that this is 0 degrees C. For some reason, it's not 25 degrees C, but it's 0 degrees C, 1 atm. And so the density of the gas at STP, the greater molar mass of a sample, so the substance that has a higher molar mass should have a greater density at the same temperature and pressure combinations. And so the higher molar mass here is O2. So O2 should have the greater density at STP compared to these other gases. If we wanted to solve for O2's actual density, we'd plug in the pressure at 1 atm is STP, the molar mass 32 grams per mole. And grams per mole is fine here if you want to get a density out in like grams per liter. So we'll look at units here as we go, but R 0.08206 liter atmospheres per mole Kelvin. Only in the one problem for velocity do we need to worry about the other units of R. So this equation here, we just go back to the usual units of R, and then 0 degrees C in Kelvin, 273.15 Kelvin. So if we want to calculate that density, you guys update your iPhones and see this new calculator? Like, how did they change the calculator? Like, what was wrong with the calculator? So it's 1.43. And then the way the units work here, the ATM cancels, the mole cancels, the Kelvin cancels. The only units not canceling are grams and liters. So it's 1.43 grams per liter. And if you make the molar mass smaller, of course, you're going to get a lower density. So helium here would have the lowest density. Oxygen would have the highest density. Okay, so just remember for velocity, if you have to calculate it SI units, everything else in this chapter predominantly is either in ATM or you're converting to ATM and using that 0.08206 liter atmosphere per mole Kelvin version of R. The greatest melting point here, this question here is kind of funny. You know, like, take 10 seconds. Which compound do you think has the highest melting point? Who says it's A? Who's really thinking strongly it's A? Be brave if you think it's great. Anyone else? I'm sure others do. You're not the only one. Who thinks it's carbon? Who's completely unsure, has no idea? Anybody brave enough? Okay. Well, like, which one of these is a solid at room temperature? It's not. So of these, radon is a noble gas. So this is a gas at room temperature. O2 is obviously a gas, and then these three are gases. To be a solid at room temperature, of course, means the substance has to have a melting point above room temperature. And so we know that carbon diamond's melting point has to be above room temperature, and the others have to be well below room temperature in order for them to have melted and then boiled at room temperature. So it's a question, I've asked this before, and it really catches students off guard. And then afterwards, like, oh yeah, that does make sense. That now, why does diamond have a higher melting point? Is that it forms that covalent network solid, that the carbon atoms here are just linking up and forming these three-dimensional arrays of carbon atoms where we get a sample where every carbon atom has 4 covalent bonds, and then it leads to another carbon atom that has 4 covalent bonds, leads to another carbon with 4 covalent bonds. You just have that structure that in order for this substance to boil, I don't even know what has to happen for that sample to melt and boil. I mean, those bonds are really frozen into like a crystal structure, so it's gonna be really hard to melt a covalent network solid. So this substance here forms that covalent network. And covalent network solids have that general property of having very high melting points and boiling points. And so the melting point of diamond is like over 2,000 degrees C, so super high for the covalent networks. Now, most of our nonmetals, they are only forming a molecular solid. So most of the other non-metallic elements that can't form that type of network solid we're only forming some type of molecular solid that's a weaker structure, doesn't have like a crystal structure, doesn't form all these covalent bonds, and so it's weaker overall. So these are all just what we call the three choices here. These are all molecular solids. So they would just form that weaker force of attraction. Okay, so so when you're looking at a choice, like if I've done this question before where it's like lithium, oxygen, fluorine, neon, which one has the highest melting point? And like lithium's a solid, and so like it has to be lithium. So when you have a question like the melting point question, try to think if you know anything about the substances. Like if I go F2, Cl2, Br2, I2 is a solid at room temperature, bromine's a liquid. You know I2's higher melting point and boiling point than bromine. And we now know it's because I2 has a stronger dispersion force. So I2, Br2, Cl2, F2, those are all nonpolar, but the bigger the nonpolar compound, the stronger that force of attraction. Okay, so what about NaCl? So NaCl, is it crystalline or amorphous? Well, NaCl, of course, is an ionic compound. Ionic compounds are generally crystalline. So it's going to form a crystalline structure. Is it molecular, covalent network, or ionic, or these other ones? It's, of course, ionic. We know that one's pretty easy. Which term would apply to carbon in its diamond form? We talked about this above. That's covalent network. An example of a molecular solid. I mean, there's a bunch. It could be like water solid, anything molecular, like even, I2 solid. So these are things that can be solid. F2 in its solid form, which is probably pretty rare to find. We have a really low temperature because it's a gas at room temperature. But just anything that's molecular. Sugar, so like C6H12O6 in its solid form, those are all molecular solids. So anything that's a molecular compound in its solid form is a molecular solid. I doubt you'll see too much about polymers, but like a polymer would be something like this, where it ends up to like 1 million or plus, really big number of repeating units in a molecule. So imagine a hydrocarbon with a gazillion number of carbons attached to it. That would be what we think of as being a polymer. And then you can add different functionality. But again, I think that the idea of a polymer is you can have a variable set of properties, variable set of molecular weights, but probably insulating in terms of its main property, because molecular compounds are insulating, not conductive at all. So our polymers generally, like plastics, are non-conductive. Melting points of ionic compounds are often found to be proportional to their lattice energies. Which compound below would be predicted to have the greatest melting point? So the compound with the highest lattice energy should be the compound, when I think of Q1, Q2 divided by D, the compound that has the higher magnitudes of charge. So the higher the magnitudes of charge go, and I always think magnitude, just so I think a -2 charge is greater than a -1 charge, right? It's less negative, or it's more negative, but it's greater in magnitude. So I want to have +2 charges, or -2 charges are greater in magnitude than +1, -1. So having higher magnitudes of charge gives us a greater lattice energy, and then having the ions closer together gives us a greater lattice energy. So we want higher charges on our ions, or we want them to be closer together and smaller. And so the compound predicted below to have the highest melting point, I see +1, -1s, a +2, -1, but I see these two here that are +2, -2s. And so the +2, -2s are going to have the overall, out of these 5, highest lattice energies, just on the basis of their charges. And then, so we just rank by charges first. If you recall, the lattice energy of +1, -1s are about 600 to 1,000 kJs per mole. The +2, -2s are about 3,000 kJs per mole. So a big difference in lattice energy based on charges, and a very small difference based on sizes. So the charge difference is what we look at first. And then when we see two compounds that have the same charges, we want the ions that are smaller to have a greater force of attraction that's going to be harder to separate, therefore higher melting point. So MgO, the difference between that and CaS, is magnesium is smaller and oxygen is smaller than sulfide. So these ions here are both smaller than in calcium sulfide. So +2, -2 is far away, easier to separate. +2, -2 is closer together, harder to separate. So higher melting point for MgO. So think about how melting a solid, we have to break some of these ionic forces of attraction. To boil the substance, we have to break them all. So the idea for melting and boiling of ionic compounds is the stronger that lattice energy, the higher the melting point. So MgO, higher lattice energy, higher melting point. Just a Lewis structure question on PO4, in which all atoms obey the octet rule, so meaning don't expand the octet of phosphorus here. So for 5 plus 4 times 6 plus 3, that's 32 electrons. That gives us a central phosphorus. 4 oxygens, lone pairs around the non-central atoms, uses up all 32 electrons, leaving none behind for phosphorus. And then if we wanted to try to make a double bond to reduce the formal charge of phosphorus, which would be plus, why is it plus? Well, phosphorus should have 5 electrons around it, and if it did, would be electrically neutral. That would be a neutral phosphorus atom. So we take the periodic table count, and then we subtract the number of electrons closest to it. It's 1/2 the number of bonding electrons, but I don't like to do the calculation that way. If you do it that way, you're taking 1/2 times 8, because there's 8 bonding electrons. And so that gives you 1/2 times 8, which is 4, gives you a charge of +1. I like to, if you recall, because it's been a while since we maybe did this, is like to break those bonds in half and maybe draw a box and just think, I'm just really trying to evaluate this atom here. What would that charge be of that atom? We might go back to a dot structure, that this is our neutral phosphorus. That's like phosphorus in the periodic table. Its charge would be neutral. And if I take one of the electrons away, that's creating a positive charge on that atom. So it should have 5. I only have 4 electrons around it, therefore it's +1. So a few different ways to get at formal charges. I think what the formal charge is representing is, if you imagine the bonds are all equally shared, what's the average charge, or what would the charge be for the atom in the structure? So +1 for phosphorus, minus for the O's, because the O's should have 6 electrons around them, and they have 7. So these are all minus charged O's. And then if we wanted to try to make a double bond to reduce the magnitudes of formal charge, we have to expand an octet. But this is kind of silly in a way, and we now have a greater understanding that likely to make a double bond, be a sigma and a pi bond, would have to have an leftover p orbital in the hybridization process, which we probably don't have. So if we go back to this structure here, this is probably a tetrahedral, and it is in reality a tetrahedral molecule, meaning the hybridization set for phosphorus would likely be sp3. With sp3, there's no leftover p orbital to make a hybrid orbital, so we would have really no model to show us how we get a pi bond between phosphorus and oxygen anyways. So I think it makes sense that we would stand pat with 4 single bonds here and just have the formal charge of plus on phosphorus. And that's good, because phosphorus is less electronegative than O, and it wants positive charge more than O does. O likes being negative, so this is a good Lewis structure for phosphate. So +1 for the phosphorus in the molecule. Let's look at MO, a couple MO diagram questions, and then we'll wrap up for today. So for MO theory, what are the bond orders of C22 plus and O22 minus? So when we're given a question on the ions of a compound, we want to go to the diagram. You get these diagrams on the test or on the sample info sheet. So for C22 plus, what I want to think about is each carbon should have 2 times 4 electrons. Then I have to lose 2 electrons to get to a 2 plus charge. So the 2 plus here requires that I subtract 2 electrons, and I only put 6 electrons into my valence diagram. So my valence diagram, and I know it's a valence diagram when I think these are 2s and 2p orbitals. This is my sigma 2s, sigma star 2s, antibonding orbital, pi 2p, sigma 2p, pi star 2p. Now the pi's are the vertical pi orbitals, and I have 2 pi bonds that are identical to each other. So seeing 2 together tells me that's the pi set. Seeing the 1 connecting to the p tells me that's the sigma. That's the orbitals that are this way. And so that's our sigma 2p. And then I get the sigma star 2p. The 1 by itself that goes up in energy is the sigma star, the antibonding orbital. So the bonding orbital, maximum density between the atoms, the antibonding maximum density away from the atoms, and then sigma, maximum density on the bond axis, pi, maximum density kind of in the plane of the bond axis. Okay, so the idea for C22 plus though is just put 6 electrons in, 2, 4, and then 6. And then the 6, I got to apply Hund's rule, put the electrons into the 2 orbitals, spin paired into the same direction. And so the bond order for C22 plus, the bond order would be a half times the bonding electrons. And so the bonding electrons are these 4 electrons here, and then minus the anti-bonding electrons, which are these 2 electrons here. So you take the total bonding minus the total anti-bonding in the diagram, and the net here for C2 is we have a single bond, that this works out to be 1. And having 1 means we have 1 pair of electrons on average between the nuclei. And so we have a single bond between the 2 carbon atoms, and C22 plus is 1. Now O2, 2 minus, O2, 2 minus, this will be 2 times 6, and then plus 2 for the negative charge. That's going to be 14 electrons. We go 2, 4, 6, 8, 10, 12, and then 14. So we fill the diagram up to 14 electrons. And then a half times my bonding electrons. So the bonding are 2 plus the 6, so that's 8 bonding electrons. And then my anti-bonding electrons, I have 6 of them. So my bond order for O2, 2 minus, is also 1. And so the answer here would be A, both of them having bond orders of 1. Now, C22 plus, is it diamagnetic or paramagnetic? 2 electrons in the same direction, that's paramagnetic. So this is para. And then B2 has the same configuration. It also has 6 electrons, also the same diagram, has the same configuration. So both of those 2 molecules would be paramagnetic. They both have unpaired electrons. And so that means they'd both be drawn into a magnetic field. All right, that is it for for where we're at in the packet today. We can continue along or take other questions tomorrow. That's our class. Not much time for a goodbye, but I appreciate all you guys who came to class this semester. Good luck on your final, and good luck beyond. So I hope to see you over the next couple days in office hours. But take care, good luck.